Hey all dear champions of civil and mechanical. Guys, welcome to BYJU'S Exam Prep. And guys, this is Abhinav Negi and me along with Dheeraj sir will be taking you over for the complete SOM formula marathon tonight. Okay, so all chapters guys, whether it is stress strain, SFD, BMD, bending stress, shear stresses, principal stresses, or you can call it transformation stress, torsion, spring, column, combined stresses, deflection, slope deflection, everything, each and every chapter, each and every formula we will be taking tonight guys. So keep sharing the video so that more and more commandos can join in guys. Okay, so complete formula we will be doing today guys. Okay, this is about me. My name is Abhinav Negi, done my MTech from IIT Delhi. This is nothing much important here. This will not be asked in the examination. Guys, at present in this YouTube channel for civil and mechanical both, we are running with the prediction series. Okay, where we are telling 10 expected questions of each and every subject. Okay, so fluid mechanics is done by Joshi sir today. Now tomorrow, that is the Republic Day, 26th of January, I'll be taking the geotechnical engineering expected questions tomorrow. Okay, so this will be tomorrow guys on 26th. Then guys, for mechanical, yes, thermodynamics will be done today, tomorrow on 26th by Sonu sir. One more series we are running right now on this channel, that is formula revision, in which strength of material is going on for civil and mechanical both. Now exam analysis for mechanical and civil will be on only on this channel guys. Expect all questions on the memory base plus safe score, cutoff, everything will be done here. And guys, this is the mega event. 3 champions, 3 days, Friday, Saturday, Sunday, 27, 28, 29. The complete marathons of verbal ability, engineering, mathematics and general aptitude will be done. Okay. Now, this will be on tomorrow, 26 mock test for civil and mechanical both. Okay. And this I've just taken. If you are preparing for engineering services, you can just see this important topics of non-tech and technical of civil. Okay. This me and Dheeraj sir will be taking this week only, do's and don'ts. This session I've just taken, and you can all find this link and important updates in my Telegram group, Civil by Abhinav sir. One more important update guys, a super duper workshop will be by Rakesh sir. It will be on 29th of January at 12:30 p.m. and it will be on app guys. Okay, 7 golden rules to secure single digit rank in GATE 2024. Along with this workshop, we are running with a mega mock challenge also, 24th to 30th January. Anytime you can give this free of cost computer based test sitting from your home only. And on 31st of January, we'll be providing you your result. Good evening, everybody. How was the Josh commandos? Everybody, please let me know in the comment section. Everybody, please let me know in the comment section. How is the Josh? Okay, okay. So, guys, these are the complete syllabus of strength of materials. The first chapter, stress and strain. Okay, each and every formula I'll be telling you here. Okay, then SFD, BMD, then bending stresses. Okay, we'll be going now. Then transformation of stresses. Up to here, I will be taking. Okay, this I will be taking. Then Dheeraj sir will be joining here only on this link only. And then Dheeraj sir will be taking torsions, pressure vessels, shear centers, and deflection of being. This part Dheeraj sir will be taking. So I'll be taking these 4 chapters. Okay, the book that you can follow for the concepts is Gary and Timchoke for strength of materials. Let me tell you the important topics of strength of material for civil and mechanical both. This session is for both. These are the important topics: stress strain, bending stresses, transformation of stress, and slope and deflection. And these are topics from which you can expect less amount of questions. Okay, so ready guys? Shall we begin? Complete SOM marathon formula. Okay, I'm not going to derive here anything because already we have taken, me and Dheeraj sir have taken a session on SOM on I guess 4th of January. You can see that where we have taken complete SOM, numericals, concepts, derivation, important points, important theorems, everything. That was 9 hours 50 minutes I guess. Okay, this session will be particularly dealing with formula only. Okay, Rishabh Pant, how are you? Rishabh Pant is also here. चोट कैसी है भाई? Rishabh Pant चोट कैसी है? चोट सही है? Okay, 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 okay. So, shall we start then, guys? Shall we start? Okay. So, let me first of all deal with here also in this test and curve also I'll be dealing with some formulas. That is why I'm taking it here. Okay, let's begin with chapter number 1. Now, suppose guys, we have a mild steel specimen. Okay, we have a mild steel specimen and I'm applying force on it. So of course SOM is dealing with deformable physics. SOM is dealing with deformable physics. So here will be some strain also. Okay, it will elongate also. Of course the literal dimension will be compressed, but I'm not going into the Poisson ratio right now. Okay, so there will be some elongation. Okay, there will be some elongation. Now stress will be P by A naught. This is the engineering stress. By default the stress is engineering stress. Force by original area. P by A naught. Okay, and strain is delta by L naught. Let the original length be L naught. So strain is delta by L naught. What is the unit of strain? It is unitless. Because above also length unit, below also length unit, it will be cancelled out, it will be a ratio. That is why it is represented as a ratio or percentage. You can write 0.0012 or 0.12%, what's your choice. Now, when we apply stress on this, first the strain and stress behavior is linear. Okay, first the stress and strain behavior is linear. Okay, this is koi zaruri nahi hai ki this will be a linear, guys. For aluminum and copper, this is not linear. For aluminum and copper, this is not linear. For mild steel, it is linear. That depends on its molecular arrangement, its molecular behavior on the application of force. Okay, it is not any concept that it will be straight only. It can be curved also. So, after A point, up to A point, it is linear. So, A is also called as proportional limit. This A point up to which it is linear, it is also called as proportional limit. After A, up to B, this is curved here. Now this is curve. Okay, and B is called as elastic limit. What does the elastic limit means? What is the meaning of elastic limit? Elastic limit means that if you remove the load at B or before B, if you remove the load at B or before B, if you remove the load here or before B, it goes to its original position. That will be whatever its original length, original dimension, it will be going there. If you remove the load at B or before B. Okay, now if you see from microscope, is there microscope here? Yeah, here. If you see this part microscopically, then what you will find that, this is a very interesting point here, that it is going right hand side. If it was a straight line here, okay, if it was a straight line here, it will be something like this, and it is going to the right hand side. After A, it is going to the right hand side. Okay, because after A, the strength of the material is not that much. Okay, strain will be more, and when strain will be more, that means it is going right hand side towards the strain, more strain. Okay, if it was straight, it was like this dotted line, but it is shifted to right hand side, that is towards strain. That means more strain is happening with increment of stress as compared to before. Okay, and if you remove the load, at B or before B, it goes into its original dimension. Okay, now C is called as upper yield point. Okay, this C point is called as upper yield point. Okay, and after the upper yield point, there is some slippage of carbon atoms. Okay, some carbon atom slips. Okay, so internal strength decreases, internal resistance decreases. What is stress? Stress is internal resistance. After say some carbon atom slips, so internal strength decreases. That is why it is falling here. D is lower yield point, and sigma y, or you call it Fy also sometimes, is corresponding to this lower yield. This is sigma y, or you call it Fy, that is yield stress. From D to E, it is called as, plastic region. What is plastic region? That at constant stress strain is happening. At constant stress strain is happening. When I was in college, मेरे को क्या गलत लगता था कि here this means that strain is happening without any force. No. It is not like that. That is fluid. Without stress, strain is happening. Here, strain is happening at a constant stress. At E, the crystalline structure of mild steel changes. Okay, and the crystalline structure changes in such a way that for further strain, it is not easy. You have to apply a more amount of stress. That is why this region is called a strain hardening region. It is hard. It is not as easy strain as like this. After E, the crystalline structure of mild steel changes. It imparts resistance for further deformation. Further deformation is not easy. It imparts resistance. So you have to apply a more amount of stress. That is called ultimate stress. Okay, the maximum stress. And ultimately, it fails at point G. That is the fracture point. And this region is called as necking region. Okay, because when it will be failing, it will be something like this, like a neck shape. Okay, like a neck shape. When in tension, not in compression. In compression, it will be a fat stomach shape, not a neck shape. While tension, the cross-sectional area decreases here. Of course, the Poisson effect, and it breaks in cup cone failure at 45-degree angle. Because at 45 degree, why the cup cone failure is at 45 degree? Can please let me know? Why the cup cone failure is at 45 degree? Please let me know. Why the cup? Can anybody tell me here? Any commando can tell me here that why the cup cone failure is at 45 degree? Why the cup cone failure is at 45 degree? Can you please let me know? Can you please let me know? Why the cup cone failure is only at 45 degree maximum shear? Okay. What about others? What about others? What about others? Others are not interested in telling me, because guys, for this, if you see the Mohr circle, okay, it will be like this. It will be like this, because at this plane the stress is P by A, and at perpendicular plane the stress is 0. So this minus stress is 0 and this is P by A. Okay, and ductile, this mild steel is a ductile element. Ductile elements fails in shear. Okay, brittle element fails in normal stress. Ductile elements fail in shear. So this is the maximum plane of shear, tau max. And from the P by A plane, it is at 90 degree in Mohr circle. If it is 90 degree in Mohr circle, so in real life it will be 45 degree. So here it fails at 45 degree. Give me yes or no in the comment section. Have you understood this? Yes, Yudhishthir Sharma, Money, everyone. Please let me know. Have you understood this? Give me yes or no. Everyone on the comment section. Everyone on the comment section. Give me yes or no. Have you understood? And guys, please share the session, yeah, so that more commandos can join in. Everyone. Everyone, come on, come on, come on. Okay. Now, the tile metal fails at 45 degree. Brittle material is failing at the plane of normal stress only, because it fails at normal stress. So this is the plane where the maximum normal stress is occurring, P by A. So it fails here only. Okay, that was the stress strain curve for the mild steel. For different materials, stress strain curve is like here. Okay, this is the stress strain curve, and for different grades of steel. Let me tell you one more important point here. Initial slope theta is Young's modulus. Okay, this is Young's modulus, stress by strain. Why? Now, can anybody tell me why? Can anybody prove this? Let me tell you. Guys, what is the equation of a straight line? Y is equal to mx plus c. And if that equation passes from origin, at x is equal to 0, y is equal to 0. So that means c is equal to 0. Y is equal to mx. M is equal to y by x. What is y here? Stress. What is x-axis here? Strain. So stress by strain is m. That is slope. Slope is what? Slope is what? Tan theta. And what is stress by strain? Young's modulus. Okay. Now, let me tell you that for different grades of steel, for different carbon percentage of steel, this is the carbon percentage, more carbon, more carbon. So when carbon percentage increases, this is less carbon in mild steel, then high yield, more carbon, then most STS steel, more carbon. Carbon percentage increases, that ultimate stress increases. This can take less stress, this can take more, this can take more. So more is the carbon percentage, more ultimate stress it can take, but ductility decreases. Ductility means, the real definition of ductility means post-elastic strain. After elastic limit, what is the strain? Okay, let me tell you in a common way, ductility means that it is failing with less strain. Yes, it can take more stress, but it fails at less amount of strain, less ductile. Okay, but initial slope is same. tan theta is same. So that means Young's modulus is constant. This is not bulk modulus. That means constant. Got it? Everybody please let me know in the comment section. And guys, rubber is a ductile material or brittle material? Rubber. This rubber is ductile or brittle? Rubber is ductile or brittle? Please let me know on the comment section. Rubber is ductile or brittle? Rubber ductile hai ya brittle hai? Everyone. Please, please, please. Please let me know. Rubber is ductile or brittle? Rubber is ductile or brittle? Brittle. Please. Rubber is brittle. Okay. So anyone can tell you, hey Abhinav, hey. Rubber is failing with high strain. Rubber is failing with high strain. Rubber is failing with high strain. Then why it is brittle? Let me tell you. Because the real definition of ductility is that post-elastic strain should be more. It should be more than 5%. Strain is in the ratio or percentage. Na? So here elastic limit is this. And post-elastic strain is less than 5%. So it is brittle. Usually other than rubber, for every other material, if it is failing with high strain, then post-elastic strain is also high. But rubber is the special case. It is failing with high strain, but post-elastic strain is less. Okay, that is why it is brittle. Everybody give me yes or no. Have you understood this? Come on, commandos, everybody. Have you understood this? Tell me. Okay. Now, let me tell you the stress strain material for brittle. Okay, this is sigma positive side, that means compression. If it is brittle, it will fail with less strain. It will not be like this. It will not be like this. Then how it is brittle, yaar? Okay, it cannot fail with high strain. Okay, it is brittle means it's failing with less strain. So it will be like this. It is failing here with less strain. Okay, it is failing in less strain. But in compression, the brittle materials are more stronger, like concrete. Hi Teju, how are you? Okay, in compression, the brittle material can take more load, like concrete is strong in compression but weak in tension. Okay. Now, guys, grade of steel I have told you. Now let me tell you aluminum and copper. So aluminum, copper, the stress strain curve is like this. Then how to find sigma yield here? How to find sigma yield? Because it is steel, it is yielding from here. It is yielding from here. So this is yield stress. It is yielding from here. But how to find sigma yielding here? Next question. What is the necessity for finding the yield stress? Why you want to find sigma y, or somebody call it Fy? The first question is that what is yield stress? And in fact, before the first question, what is the necessity for finding the yield stress? The necessity is that the permissible stress on any material is sigma y by factor of safety. Factor of safety you can decide on the basis of importance of that structure. Okay, might be you are making a temporary structure, factor of safety may be less. Might be you are making a structure for Commonwealth Games or World Cup or Rashtrapati Bhavan, factor of safety will be more. Okay, so of course technically or logically or engineering service interview point or IIT MTech interview point, factor of safety will not be depending on Rashtrapati or a common citizen. It should be same. But if you are making a temporary structure, even for Rashtrapati or anyone, factor of safety may be less. Okay. Now, for finding sigma permissible, sigma y is required. That is the necessity that we want to find sigma y. So, where there is no yielding, what we do here, we go to a 0.2% strain. 0.2% strain means 0.002. Initial slope of this line is theta. So from theta, from here with the angle of theta, we go here. So whatever this value is coming, that is called 0.2% proof stress. That is called 0.2% proof stress, or it is called as yield stress. Now somebody can say, sir, why it is 0.2%, not 0.25%, not 0.15%? Because guys, there is no logic, there is no derivation on that. An engineer has two eyes. Of course, everybody has two eyes also. Computer science also has two eyes. I'm not considering them as engineer. Okay, just kidding. So engineer has two eyes. One eye is economy, one eye is safety. Whenever the mechanical engineers are designing a machine or civil engineering is designing a home, then we have to be economical and safe also. Both should be done. So with 0.2%, the sigma y is coming like that. That sigma permissible comes to be like that. We are economical and also and safe also. Okay, that is how it is taken like this. Okay, have you got it? Got it, guys? Everyone, please let me know. Everyone, please let me know. Every commander. Understood? Please put a heart sign on the comment box if you got it. And if the worst or if the hardest of the question is coming from here, if the hardest of the question is coming from here, what it can be, they might be giving you the equation of this yellow line. Okay, they might be giving you the equation of this yellow line. Sigma is 2 epsilon square minus epsilon plus 3, something like this. Okay, and they are asking that what is 0.2% strain. So what you will do, find the slope at x initial. So d sigma by d epsilon, that is 4 epsilon minus 1. Okay, let 4 epsilon plus 1 at origin, slope is equal to plus 1. Okay, now equation of a straight line is, what is equation of a straight line? Equation of a straight line is y minus y1 is equal to mx minus x1. Now m is plus 1. I'm just giving an example, not going into the accurate values. Okay, proof resilience register, we'll see later. Now what is y1 here? This point, y1 is 0. What is x1? 0.002. So you will find the equation of this green line by putting these values. Now solving green line and yellow line, solving this green line and yellow line, solving this, the y coordinate will be sigma y. Understood the concept or not? This may be the hardest question that can be asked from here. Have you understood this? Have you understood this, my champions? Can you please let me know? Can you please let me know? Come on, come on, come on, come on, come on. Everyone in the comment section, please put a heart sign if you got it. Please put a heart sign if you got it. Please put a heart sign if you got it. Okay, this level of concepts we are dealing in the BYJU'S exam prep, guys. You will not be finding this anywhere else. And let me again remind you, if you want complete derivation, numericals, concepts, theorem, proof, laws, assumptions, then already we have taken a marathon in this month only of 9 or 50 minutes. Okay, this particular session or marathon is only dealing with formulas. Okay, so stress matrix will be like this. Sigma xs tau xy. Now what are the number of elements? Different number of elements. Total number of elements 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. What is distinct? Please let me know in the comment section. Yeah, distinct are 6 because adjacent. Oh my god, from the charger I may be falling. Okay, because this tau xy and tau yx are same. Okay, this tau xz, this adjacent faces stresses are same. Now how this come in that marathon we have already told. Okay, this is only dealing with formulas. Tau zy and these are same. Actually the stress matrix is a mirror image about the principal diagonal. About the principal diagonal, this is a mirror image and this is due to moment equilibrium. Adjacent faces stresses are equal due to moment equilibrium. What is the order of stress tensor? What is order? We are dealing with formulas, guys. I'm not going what is this, how we have derived this. In that marathon we have done this. In that marathon, what is the notation, this, everything we have done this. This is only formula. So total are 9, distinct are 6 because we know 1, 2, 3 and either of this only one is required. Either of this only one is required, because other is same. Either of this one is required. So total are 9 but distinct are 6. Anyhow, these two are same. Order of stress tensor is order of stress tensor. What is order of stress tensor? 2. Okay, you write like 3 की power x is number of total elements 9. So whatever the value of x, that becomes order of tensor. Okay. Hi Akhil, how are you? Akhil bhai share kar dena yaar. Okay, and like this we have strain also. Okay, strain is, okay, what is normal strain? What is normal strain? Change in length by original length. What is shear strain? Suppose lamina is like this and we are applying the shear stresses. So after application of shear stresses, this deformed like something like this. Earlier the angle is 90, now the angle is changed by gamma. So gamma is the shear strain. This deformation, the change in angle is shear strain. And of course this is gamma by 2, this is gamma by 2. Because all tau are same, na? Tau 1 equal to tau 2 equal to tau 3 equal to tau 4. So half change will be here, half change will be here. If total angle change is gamma, either it is decreasing or increasing, because here also it is increased. So it is half on both sides, because why half on both sides? Why symmetric? Because tau 1 equal to tau 2 equal to tau 3 equal to tau 4. Now there are 4 elastic constants for isotropic material. There are 4, but distinct are only 2. Distinct are only 2. Because if suppose we know K and mu, so E will be find out. Once E is find out, we already know mu, so G can also be find out. So any 2, that can be, if K and G are known, E will be known. If K and G are known, mu is known. Okay, so these are the relations between the elastic constants. What is Young's modulus? Stress by strain. But this is only valid when the load is applied on unidirectional. Okay, stress by strain will be Young's modulus only when the load is unidirectional. Okay, now shear modulus is shear stress by shear strain. Mu is minus of lateral strain by longitudinal strain, and K is hydrostatic loading sigma when the all stresses sigma in 3 directions are same. In that condition, what is the volume change? Volumetric strain, that is the bulk modulus. Now, can you please let me know, in isotropic material, only total are 4, E, G, mu, K. Total are 4, E, G, mu, K. And distinct are any 2, because from any 2 we can find remaining 2 also. For isotropic, distinct are 2. For orthotropic, distinct are 9. For anisotropic, distinct are 21. Got it? Got it? Okay. Now we are dealing with only formulas, so I'm not going here. The values of mu is like this. Now if they ask the value of mu of metals, okay, the value ranges from 0.5 to 0. If they ask mu for ductile metals, these 3 different questions can be asked on the range of mu. 3 different questions can be asked on the range of mu. So mu of ductile ranges from 1 by 3 to 1 by 4, 0.25 to 0.3. And if they ask mu for all substances in this word, so it can be maximum is 0.5. Okay, and this can be -1. Okay, so 3 different answers can be there. 3 different answers can be there. It depends on what in the question they are asked. Hello Arun, have you understood this? Please put a heart sign on the comment box if you have understood this. Come on champions, everyone. Many students come to me, sir. See, different answers are there, sir. Guys, different answer is not there. Different questions is also there. That depends on mu of metals or mu of ductile metals or mu of all substances in this word. Nobody is putting the heart sign here. Come on, except Arun, nobody is putting here. Nobody is putting here. Come on, yaar. Come on, show some josh, yaar. I'm teaching from the whole day. I have the energy. Where is your energy, guys? You are the young ones. Okay. Okay. Excellent, guys. Now, moving for the guys, mu of rubber is 0.5 and also mu of plastic materials. Okay, mu of plastic material. There is a reason behind that. Let me tell you that also. Guys, volumetric strain, that is delta V by V, is given by sigma x plus sigma y plus sigma z into 1 minus 2 mu by E. Now for rubber, mu is 0.5. Mu is 0.5, so it will always be 0. So there will be no volume change for rubber. For plastic material also, the volumetric strain should not be there. For plastic material, guys, volumetric strain should not be there. Let me tell you one important thing. Might be you might not be knowing. Guys, in this region, there is no volume change. No volume change. It is plastic region. Okay, now you are saying, sir, length will be increasing, sir. So how volume is not changing, sir? So length is increasing, sir. So strain is there. Guys, other dimensions are contracting also, na, due to Poisson effect. So this is the plastic run. In plastic region, there is no volume change. So for every time in question, if they ask what is the value of mu for plastic, so you should be applying a brain, applying a trick. They have asked the mu for plastic, and the plastic material volume is not changing. Volume is not changing. So mu should be 0.5. Okay. Foam, soap foam, human tissues, soap polymer, everything is negative. Okay. Now, guys, moving forward, suppose, leave this. Suppose this is a body, and in this body, suppose this is sigma x, this is sigma y, this is sigma z. Okay, I am saying suppose this is y direction as usual, this is x, and the axis that is coming out of the camera to your forehead, that is the z axis. Okay, and stresses are like this. So epsilon x is sigma x by E minus mu sigma y by E minus mu sigma z by E. That is the length change in x direction upon the length in x direction. Sigma y, epsilon y is equal to sigma y by E minus mu sigma x by E minus mu sigma z by E. That is the change in length in y direction upon the length in y direction. Similarly, epsilon z also. And volumetric strain, I have given one formula here. Volumetric strain has one more formula. Volumetric strain has one more formula, that is epsilon x plus epsilon y plus epsilon z. In fact, I'm not going direction. When we add these three, then only this relation comes. Have you got it? Have you got it? Okay, can you guys please everybody write down your states or cities, from which city you are watching me right now? Everyone. Everyone, let us see that from which part of the country the people are here. Hyderabad, Rajasthan, UP, Allahabad, Chennai, Junagadh, Gujarat, Ahmedabad, Vellore, Patna, Madurai. Okay. So now, guys, volumetric strain is strain in the three directions. So here, epsilon longitudinal direction here, and these two, this and this, both are the same. That is the diametric strain. Guys, in cylinder, okay, this is one direction, that is the longitudinal if force is acting here, and these and this both are same, that is epsilon diameter. So it can be like this. And sphere, because volumetric strain is epsilon x plus epsilon y plus epsilon z, na? In sphere, all the three directions are similar, so it will be 3 into strain in any one of these directions. Okay. Now, impact loading, you just have to know this, that when you are applying a load with negligible height, the stress in that case will be 2 times of stress static. Sigma dynamic or sigma sudden or sigma impact is 2 times of sigma static. If W load is only acting on A area, okay, so it will be W by A. In case of sudden, I'm not going in derivation because I already told you this in the original marathon. It will be 2 times of WA, but it will be when H is 0. It will be when H is approximately 0. Okay, otherwise you have to calculate from this quadratic equation. Now, what is the elongation, guys, when a P load is acting? Delta is PL by AE. Delta is PL by AE. Of course, here the bar is considered weightless. In all this formula, the bar is considered as weightless. Okay, what is the stiffness? Stiffness of a spring is given by P by delta. Okay, stiffness of a spring is given by P by delta. So same if I'm comparing this with the bar. Same I'm comparing with bar. So it will be P by delta. What is delta? What is delta? PL by AE. Okay, so it will be P by delta. It will be AE by L. So stiffness of bar is given by AE by L. And what is compliance? Compliance is flexibility, that is reciprocal of stiffness. So it will be L by AE. And what is axial rigidity? What is axial rigidity? If somebody asks you what is axial rigidity, so axial rigidity is AE, because if AE is more, delta will be less. If AE is more, delta will be less. So it is providing rigidity to the bar. Okay, in all these formulas, delta is equal to PL by AE, the bar is considered to be weightless. Okay, now guys, suppose there is no load acting on the bar due to self weight. Due to self weight, the elongation is lambda L square by 2E. Okay, due to self weight, it is lambda L square. Lambda is unit weight. Lambda is unit weight, that is weight by volume. Okay, of course not going in derivation because this is only formula revision. Lambda L square by 2E. And if you calculate it from here, if you put lambda is W by volume, volume is W by A into L. If you put this lambda is W by AL here, okay, it will be WL by 2AE. Here W is not external load, W is self weight. Okay, W is self weight. That means if W load is acting on a bar, on a weightless bar, what is the deflection? If W load is acting on a bar, if W load is acting on a bar, what is the deflection? WL by A. If there is no load acting on the bar, due to its self weight W, elongation is half, WL by 2A. Okay, elongation is half, WL by 2A. Got it? Got it, everyone? Got it, everyone? Please let me know. Okay, now conical bar, the deflection is given by the conical bar, the deflection is given by lambda L square by 6E. Lambda is its unit weight. Lambda L square by 6E. It is also written sometimes for in NAT type of problem that deflection of a conical bar is 1 by 3 of deflection of prismatic bar of same length, same material. Okay, it is lambda L square by 2E, it is lambda L square by 6E. So that is 1/3 of that. Understood this? Guys, keep sharing so that more and more commandos can join in here. Everybody guys, have you shared? How many of you have shared this video here? Come on. Come on, champs. Okay. Now, when there is a tapered bar having diameter D1 here and D2 here. So deflection in that case is 4PL pi E D1 D2. Of course, not going in derivation. 4PL pi E D1 D2. If, can you tell me D equivalent? D equivalent means if a constant diameter which is having same deflection, delta same as that of tapered bar. So what is that D equivalent? That D equivalent is under root D1 D2. That is the geometric mean. That is the geometric mean. Okay, that is the geometric mean. Under root D1 D2. Okay, if we take a bar of same length L, application of same force P, okay, same material E, then for the constant diameter bar which should be having same deflection as tapered bar, D equivalent is this. If somebody has taken the average diameter D1 plus D2 by 2, if somebody has taken the average diameter D1 plus D2 by 2, his deflection will be lesser. Okay, strength of bar should be that whatever is the maximum axial stress coming on that, okay, whatever is the maximum axial stress on coming on that, the strength should be more than that, so that it should not be failing. Okay, now भाई मैं स्ट्रेस बता सकता हूं ना शाह साहब, मटेरियल मेरे को पता नहीं है, कुछ पता नहीं है, तो स्ट्रेंथ कैसे बता सकता हूं? मैं तो स्ट्रेस बता सकता हूं और ये बता सकता हूं फॉर सेफ्टी व्हाटएवर इज द मैक्सिमम स्ट्रेस इज कमिंग, it should be more than the stress. If we are considering only axial deformation, no torsion, no bending, then okay. If somebody takes the average diameter, that is D1 plus D2 by 2, so arithmetic mean is more than geometric mean, so his deflection will be lesser because actual result comes from geometric mean. if somebody takes arithmetic mean, that means arithmetic mean is bigger. That means diameter is bigger. So his deflection will be lesser. Okay. So this is for tapered bar, and when for a constant thickness width is changing from B1 to B2, then deflection is given by PL log base to the E B2 by B1 E into T B2 minus B1. Okay, if there are two parallel composite bars, then E equivalent is given by this formula. Okay, E equivalent is given by this formula. Understood? 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 Okay. Now, what is strain energy? What is strain energy? Let me tell you. Guys, everyone please see. Here's a complete concept I am telling you. Complete concept I am telling you. See, suppose this is a bar. I apply a P force here. Since SOM is a deformable physics, it is not a rigid body physics. So here will be some deformation. So we have done some work. We have done some work. That work has stored as strain energy. Okay, I have done some work. That work has stored as strain energy in my cheeks. I have done some work. That work has stored as strain energy released. I have done some work. That work is stored as strain energy. Now strain energy is released. So that work done is strain energy. So what is work done? F dot D. So F dot D, so you will be saying P into delta. Force is P, deflection is delta. No. This is the, guys, by default in SOM, every time Hooke's law is valid. Material is homogeneous, isotropic. Hooke's law is valid. Stress by strain is Young's modulus. And load is static. These are all the assumptions by default in SOM. Static load means the load you are not applying directly P is not impact load. Okay, you have applied load 0, little bit more, little bit more, little bit more, little bit more than P. That is the static loading. So the average work done is force into distance, F dot D. So average force is not P. 0 force, little bit more, little bit more, little bit more, little bit more, little bit more than P force. So average force is 0 plus P by 2. This is F dot D. So it is half P delta. So area of P delta curve, more P, more delta. Area, half base into height. Area of P delta curve is strain energy. This is strain energy. Similarly, in torsion, it will be half T into theta, pi. Here it is half P into delta. In torsion, instead of P, it will be torque. Instead of delta, it will be twist. In axially loaded bar, with P, there will be delta. In torsion with T, there will be phi, twist. So there will be half T theta. That is resilience also. Okay, that is resilience. And a more resilient material will be good for springing action. Bikes and shockers of a car should be made of those materials which are having good area. Larger area means it can absorb more energy and can release. Okay, so this is half P into delta. Now see one more thing. If I am making for a linear elastic material, stress strain is also linear. So this is P by A. P by A. This is delta by L. Delta by L. So this area, half base into height. Okay, half strain can be written as sigma by E into sigma. So this is half sigma square by E. This is strain energy per unit volume. This is strain energy per unit volume. Because denominator area, denominator length. So P and delta are making strain energy. So denominator area into length means volume is also coming. So here if it is strain energy, in denominator here area into length. So here it is strain energy per unit volume. This area is called modulus of resilience. More modulus of resilience means more area means that it is good for springing action. It can absorb more energy. And this can be non-linear also. This, even if it is non-linear, then that area is also called modulus of resilience. Have you got it? Okay. Similarly, guys, there is toughness also. Similarly, guys, there is toughness. When resilience or this is up to the elastic limit. If we are going up to the full, up to the fracture, this total area is called modulus of toughness. This total area is called modulus of toughness. This total area. and it is sometime approximately written as this is sigma y, this is sigma u. So average stress you can write as sigma u plus sigma y into the total strain here. This is modulus of toughness. And what modulus of toughness represents? Modulus of resilience represents more area means it is good for springing action. It can absorb more energy. Modulus of toughness means which is having more area, more modulus of toughness. That means the more energy is required to break it, because we are considering here up to fracture. So which is having more area, that material should be having more energy has to be applied to break it. Okay, like suppose it is steel. Steel is ductile, so area is more. Okay, cast iron is brittle, so area is less. So this A1 here is great, it is also fracture, A2. So A1 is greater than A2. This is for steel, this is for cast iron. So that means steel is more tougher than cast iron. To break the steel, more energy is required. Have you got it? Have you got it? Please let me know. Please let me know. Okay. So this is chapter number 1. This is chapter number 1. Have you understood this? Everyone, everybody, every commando. Now types of beams, one side is fixed, that is free, that is cantilever. Okay, here it is pin, here it is lower, simply supported. If the cantilever, here is support, it is a propped cantilever, fixed beam, more than 2 supports, continuous. Bending moment slope, chapter number 2. Slope of bending moment is shear force. Okay, slope of V means shear force. Slope of shear force is load intensity. इस चैप्टर में फॉर्मूला है ही कहां यार? इन दिस चैप्टर देयर इज नो फॉर्मूला. ओके ओके, स्टिल लेट मी टेल यू, इफ लोडिंग डायग्राम हैज degree n, then SFD will be having degree n plus 1. Okay, BMD will be having degree n plus 2. Okay, because one time differentiation degree is reduced by 1 na. Suppose it is x4, x की power 4. What is the differentiation? 4x cube. Degree is reduced by 3. 4x3, 4 into x की power 3. Differentiation 12x square. Degree is further reduced by 1. So if this degree is, m degree is n plus 3, n plus 2. So v degree will be 1 less, n plus 1. If this is n plus 1, then differentiation degree is reduced by 1. It will be n. So after differentiation, degree is reduced by 1. After differentiation, degree is reduced by 1. Got it? Got it? Okay, now here, guys, what is the degree of slope? What is the degree of slope? What is the degree of deflection? Can anybody tell me? This is n plus 4, n plus 3. How? How, sir? Because you will see, Dheeraj sir will be telling you that d2y by dx2 is m by ei. That means differentiating y, that is deflection, deflected curve, 2 times. Okay, y को 2 बार differentiate करने से, differentiating y 2 times, y को 2 बार differentiate करने से m आया. तो अगर m का डिग्री n plus 2 है तो इसका n plus 4 होगा. भाई y को differentiating 2 times y, we are getting m. That means degree should be n plus 4, then this degree will be n plus 2, reduced by 2 times. And theta is dy by dx, slope is dy by dx. So if this degree is n plus 4, then slope is 1 less, n plus 3. Got it? Please put a heart sign on the comment section if you got it. Please put a heart sign on the comment section if you got it. Please put a heart sign on the comment section if you got it. Now, what is contraflexure? What is contraflexure? Where bending moment changes sign. Where bending moment changes sign. See, if BMD is something like this, this is not contraflexure. It is 0, not contraflexure. Not contraflexure. No. If BMD is like this, plus and minus, this is contraflexure. Yes, this is contraflexure. Why? Oh, what is this, sir? What is this? Let me tell you. Suppose a beam here is like this. Positive bending moment, positive moment. That means sagging. So deflected shape is something like this here also and here also. So tension steel, because concrete is weak in tension. So tension steel will be at bottom only. But here it is positive. Suppose this is beam. So it is positive here. Negative means hogging. So here steel is here because tension is here. Concrete is weak in tension, so we'll putting reinforcement. It is tension here, so tension here. So counterflexure represents where the direction of tension reinforcement changes. So which is not here. That is why it is not counterflexure. It is here. That is why the correct definition is not like where bending moment is 0, that is counterflexure. No. Where bending moment changes sign, that is counterflexure. And since bending moment slope is shear force, so wherever shear force is 0, bending moment is either maxima or minima. If dy by dx is equal to 0, that means at that point either it is maxima or minima function value. And one more point I want to tell you here, that for a symmetric beam and symmetric loading, SFD is anti-symmetrical and BMD is symmetrical. Whatever case you can take it. Understood this? Please bata do yaar comment section pe. Okay. So moving further, this test and stain, everything is done here. Okay, yeah, one more thing is left here. This is we have done. Done. This is left. Okay, guys, when this is fixed due to increase in temperature, what is the stress? E alpha delta T. What is the stress? E alpha delta T. If you are increasing the temperature, stress will be compressive. If you are decreasing the temperature, stress will be tensile. Okay, SFD BMD is also done. Now I am going to the bending stresses. A very less formula here also. Then I'll be going here. Then after this Dheeraj sir will be taking. All this part Dheeraj sir will be taking. Okay, now formulas are very less. Strength of material is not like other subjects. Okay, it is not much of formulas here. It is much of concepts in strength of materials, much of numericals. Okay, enjoying till now? Please let me know. Guys, mock test will be tomorrow for civil and mechanical both. CE and ME both. Complete 65 questions as per gate pattern. Complete 65 questions exactly as per gate pattern. Okay. Now, coming here, what is this, guys? Suppose this is the cross section of a beam. Suppose this is B, suppose this is D. Where is the neutral axis in elastic case? In elastic case means when stress and strain is linear, there is no constant phase coming. So where is the elastic case? In elastic case, the neutral axis is at the centroid. Elastic case means here this one. That is our SOM. Okay, we are not going in. This is the plastic case. This is the elastic case. Now, due to, suppose this is the beam, due to application of moment, here comes compression and tension. And for, of course, for hogging, tension can be at top also. Now, see here, the bending stresses are like this. These are the bending stresses. Okay, for sagging, this compression here, this tension here. For hogging, it is vice versa. For hogging, it is vice versa. Okay, tension here and compression here. Okay, Yes, Dheeraj sir is also here, the champion of the champions. Okay, so Dheeraj sir will be coming from torsion. Now, what is this formula? That is sigma at y distance from neutral axis, maybe y at top or maybe y at bottom from neutral axis. What is the sigma? Sigma is the bending stress at y distance from neutral axis. Sigma is the bending stress at y distance from neutral axis. M is the bending moment at that location. I is the moment of inertia of that cross section. E is the Young's modulus and R is the radius at which this beam is deflecting. This will be some radius. This is radius R. Okay, this is R. And guys, let me tell you about this formula more. Suppose this is a beam. I'm not showing loading, I'm not showing supports. I'm not showing loading, I'm not showing supports. Suppose BMD is like this. Suppose neutral axis is like this. So I want bending stress at point P. Sigma P. Okay. So y is the distance from neutral axis upon y. M should be not this one, not this one, not this one, not this one. M should be about this one. This one M. Let it be M dash. I is the moment of inertia about neutral axis. Like this you have to do. E is the Young's modulus, R is the radius. Okay, like simply supported beam. If this is simply supported beam, then here the bending stress will be 0. Because at simply supported, all these are M is 0. The father is bending now here. This stress is not P by A, force by area. This is not his force by area. This stress is not force by area. This stress is coming due to M movement. The father is M here. Pitaji M hai. And in simply, if it is simply supported beam, bending moment here is 0. So in all these places, whatever the Y, sigma will be 0 because M is 0. Okay. Now, moving, please see here. One more thing I want to tell you here. For prismatic beam, prismatic means EI is constant, and pure bending. Pure bending means M is constant. Guys, in pure bending, what is the shear force? Can you please let me know in the comment section? Can you please let me know in the comment section? For pure bending, what is the shear force? For pure bending, what is the shear force? For pure bending, what is the shear force? 0. For pure bending, the shear force will be 0. Because M is constant, na? Shear force is dm by dx. If M is constant, shear force will be 0, of course. So for prismatic beam and pure bending, deflected shape is circular. Deflected shape is circular. Why? Let me tell you guys. M by I is equal to E by R. M by I is equal to E by R. So from here 1 by R is M by EI. 1 by R is also called as curvature. So curvature is M by EI. So for prismatic beam, EI is constant and pure bending, both conditions are there. M is also constant. So M constant and EI constant. That means this whole term is constant and 1 by R is constant. That means R is constant. R is constant means circle. So always for a pure bending and a prismatic beam, the reflected shape is circular. Okay. Now one more concept. Everyone. Sigma by Y is equal to M by I. Sigma is equal to M by I into Y. So what is the maximum value? M max. So M is sigma max is coming here. So M by I into Y max. So sigma max is M into I by Y max. I by Y max is called as Z, that is section modulus. So from here M, also called as MOR, is sigma max into Z. Moment of resistance is sigma max into Z. Z is section modulus. Sigma max depends on material and this depends on shape. Okay? And Z of I section, Z of I is greater than Z of rectangle, is greater than Z of square, is greater than Z of circle. Okay? Okay, that means, see, moment of resistance means how much bending moment this beam can resist. Moment of resistance means how much bending moment this can resist. The max for safety, the maximum bending moment that should be coming in the beam should be less than moment of resistance. Moment of resistance should be more, that this much movement it can resist, and whatever is coming, it should be less. Like sigma permissible is more, sigma coming should be less for safety. And I section is very good in bending, and reason being that I section is very good in bending because the area is more where bending stresses are more. Bending stresses are more at top and bottom, and their area is more. Good design for bending. For shear we'll see it is poor. And circle is the poorest section because where the bending stresses are more at top and bottom, their area is less, bekar. And where stresses are less, their neutral axis area is more. So circle is poor in bending. We'll see it is good in shear. Please put a heart sign on the comment box if you got it. Please put a heart sign on the comment box if you got it. Everyone. Nobody is giving comment here. Very bad. इस पूरे सिंगल पेज में मैंने पूरा बेंडिंग पढ़ा दिया. पूरा बेंडिंग पढ़ा दिया मतलब पूरे कॉन्सेप्ट आपको बता दिए. शेयर में बताऊंगा ना भास्कर, पूरे सिंगल पेज में. राइटिंग अच्छी नहीं है कोई बात नहीं, आपके पास नोट्स है मेरे को पता है, पर इस पूरे पेज में बेंडिंग के सारे कॉन्सेप्ट बता दिए. अच्छा, एक कॉन्सेप्ट बच गया, कि सपोज इफ दिस इज अ वुड सेक्शन and I want to convert this in steel, then depth will be same but width will be required less. If this is B here, it will be B by M. M is Young's modulus of steel by Young's modulus of wood. Guys, steel is stronger material, na? So instead of wood, if you want to replace equivalent steel section, less steel will be required. And if instead of steel we want to replace wood, then more wood will be required. Wood is weaker. How much? M times more. So B by M into B, it will be B. Okay? Like this. Got it, everyone? Okay. Now, shear stresses in beams. Guys, suppose we are going from Bhopal. When I was in offline, I used to teach sometimes, not always. Morning Bhopal, evening Indore. Suppose this is 200 kilometer. Suppose it takes 4 hours. So we average speed is 50 kilometer per hour. But this is average speed. Actually, at a certain instant, my driver speed may be 80, maybe 120, maybe 0, maybe 30, maybe 40, maybe 55. Okay, this V distance by time is the average speed. Similarly, suppose if I cut a section here, name this as 1, name this as 2. If I'm drawing the free body diagram of 1, only showing the forces, no movements. Only showing the forces, no movements. So this is RA. It is like this. So for equilibrium, RA is downward. For equilibrium, RA is downward. What is tau average? Shear force by area, RA, area is B into D. This is average shear stress. This is average shear stress, not the actual shear stress. In this chapter, we will be finding the actual shear stress. Shear force by area is average shear stress. What is the actual shear stress? What is the actual shear stress is given by this formula. Suppose we want to, this is the neutral axis. I want to find out shear stress at this P point, or let this be T point. Then cut a cross section. Then shear exactly at T point. Distance exactly at this speed, average speed is 50, but I want speed exactly here, exactly here, exactly here. Similarly, I want to find the shear stress exactly at T point. Now, here the shear stress is given by S. S is the shear force at that location. See, from right hand side is RB. A is the area above that. Okay, and if T is below, then area will be this one. Okay, area is above that. Y bar is center of mass is suppose this. So Y bar is this. Y bar is this. I is the moment of inertia about neutral axis and B is the width. This is the actual shear stress. This is the actual shear stress. And when we apply this formula for rectangular or for anyone for circular, then shear stress always comes 0 at top and bottom and a parabolic radiation. Okay, shear stress always comes. Now this is the average shear stress, constant. Actual shear stress comes from this formula, 0 at top and bottom, parabola. For guys rectangular, this is important, my numericals comes from here. Tau max is 3 by 2 of tau average. Here circular, tau max is 4 by 3 of tau average. Okay, for triangular, it is always 0 at top and bottom. Actual shear stress, actual shear stress. Tau max here is also 3 by 2 of tau average. Here in rectangular, tau max comes at neutral axis. Tau max comes at neutral axis. Tau max comes here at mid depth. Mid depth. Neutral axis is not mid depth. If this is h height, neutral axis is central axis. That is not h by 2. Neutral axis is 2h by 3 from here and h by 3 from here. Here tau max comes at mid depth. Suppose there is a I section. So how the shear stress comes? 0 at top and bottom always. 0 at top and bottom, actual shear stress. Like this, area is reducing, so stress is increasing. Area is again increasing, so stress reducing. This is tau 1, this is tau 2. Tau 1 is the stress in the flange. Area more, so less stress. Tau 2 is the stress here. Tau 2 is the stress in the web. Okay? And tau 2 by tau 1 is B by B. B is this and B is this. Now, I section is very poor in shear because where shear stress is more, I is having less area. Where shear stress is more, I is having less area. Circle is very good in shear because where the maximum shear stress are there, there is the maximum area. Please put a heart sign on the comment box if you got it. Please put a heart sign on the comment box if you got it. Please put a heart sign on the comment box if you got it. Please put a heart sign in the comment box if you got it. Teju, Bhaskar, Rajat, Arun, enjoying the session? Enjoying the session? Okay. Now I'll be dealing with this. Then here Dheeraj sir will be coming. Dheeraj sir will be coming from here for torsion, shear center and all this. Okay. Okay. Now, before going to this part, please tell me that if this is a floor and in this floor, suppose this is a body. Now, please tell me if I am applying a P force here. Normal stress is coming or shear stress is coming? Exactly at center of mass. Normal stress will come or shear stress will come? Normal stress will come or shear stress will come? Rajati sir is saying normal. What about others? What about others? Normal will be coming or shear will be coming? What about others? So many students are watching this. Normal. Venkatesan is saying normal. Ajay is saying normal. Guys, that depends on the plane. If the plane is like this, on x-axis, only normal stress is coming. Shear stress is not coming. Okay? If you consider an inclined plane YY, then on YY plane, normal stress will also coming and shear stress will also coming, because on this YY plane, because in this YY plane, this P force on this YY plane, this P force has two components. P1 causing normal stress, A of YY, and this P2. P2 is causing the shear stress on YY. Have you got it? So there are how many planes? Arun, good. There are how many planes in this body? In this body, there are infinite planes. Infinite planes will be having infinite normal stress and shear stress. Infinite planes will be having infinite normal stress and shear stress. Out of those infinite planes, the plane which is having maximum normal stress is called as major principal stress, represented by sigma 1. Out of those various various planes, the plane which has minimum normal stress is called as minor principal stress, and which is major and minor. Major means the plane which is the maximum stress. Minor means which is the minimum stress, are called as principal stresses. The biggest is major, the smallest is minor. And the planes in which this is acting are called as major principal planes and minor principal planes. The plane where the maximum normal stress, that is major principal stress, is acting is called as major plane. The plane where the minimum principal stress is acting, that is called as minor principal plane. Now, friends, where the major and minor principal stress are acting, on those planes shear stress is 0. How to remember this? Let me tell you. If a boy is first in the class, he will be having no girlfriend. Boy is sigma, girlfriend is shear. No girlfriend. That is why he comes first in the class. If he is last in the class, then also he will be having no girlfriend, no girl will be interested in him. Maximum marks of boys, maximum sigma, tau 0, no girlfriend. Minimum marks of a boy is minimum sigma, tau will be 0. But opposite is not true. Might be the tau is maximum. The girl comes first. She can have boyfriend or even not boyfriend. Both cases can be there. Girls are very hardworking. They can have both. So if sigma is maxima minima, that is major and minor, tau is 0. But if girl comes first, tau is maxima, she can have a boyfriend or even may or may not be having a boyfriend. Both cases can be there. Understood? Now, if on a plane sigma x is given, okay, if on a plane this is sigma x, okay, and this is sigma y, and shear stress is tau xy, of course all shears are same, all shears are same. Then on an inclined plane theta, then on an inclined plane theta, what is sigma x dash, what is sigma y dash, and what is tau x dash y dash, that are given by these expressions. Because I told you that there are infinite planes in a body. Infinite planes are having infinite normal stress and shear stress. And those normal and shear stress are given at different theta, these are the values. And always remember, sigma x plus sigma y is sigma x dash plus sigma y dash, and it is equal to major principal stress and minor principal stress, because major and minor are also at 90 degrees. If you add this plus minus cancel, this plus minus cancel, it will be like this. On rotating, at 1 theta, this tau x dash y dash will be 0. At 1 theta, this is 0. Okay, this is 0. That will be that theta will be principal plane, because principal plane here is 0. And once you put it 0, just in 2 steps you will be getting tan 2 theta p is equal to 2 tau xy upon sigma x minus sigma y. Tan 2 theta p, if you put it 0 na, you will get this expression. Why it is theta p? Because shear stress is 0 on principal planes. Now if you put this theta p here, now you put this theta p here, so these stresses will not be ordinary stresses, because you are putting the angle of principal plane. If you put this theta p here, you will be getting principal stress. Sigma 1 is major slash, this is not divide, this slash, sigma 2 is minor, sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 whole square plus tau xy square. Even, let me tell you, this term is also maximum shear stress, tau max. Otherwise you can do d tau by d theta here, d tau by d theta here, you will be getting the maximum shear stress. Got it? Sir, in the inclined element, stress in x direction is normal stress na sir? This one na? Yes, it is normal. Find principal stress. Yes, this is the principal stress na, Arun. From here find the theta where tau is 0. So tau 0 means principal planes. Now put this theta here, it will be principal stresses. Okay. Now if you want to draw the Mohr circle, these are from the equations. If you are drawing the Mohr circle, then center will be sigma x plus sigma y by 2. Center will be sigma x plus sigma y by 2 comma 0. Now sigma for tension it is positive, for compression it is negative. For tension it is positive, compression is negative. If one is plus 3, another is minus 3, center will coming at 0. Okay, this is the radius. Okay, and radius is also tau max, because this is radius na, radius is also tau max, radius is also tau max, this is radius na, so this is tau max also. And if this is sigma 1 major, out of the various, what Mohr circle represents? What Mohr circle represents? In Mohr circle there are infinite points. In Mohr circle there are infinite points. In Mohr circle there are infinite points. So infinite points having infinite coordinates. So infinite normal stress and infinite shear stress. So this, see, there are infinite planes na. Infinite planes are having infinite normal stresses and infinite shear stresses na. These infinite normals and shear stresses are represented by this. Okay, so the body has infinite planes having infinite normal and infinite shear stresses. Those are represented by these points. Out of the various points, this is the maximum normal stress, sigma 1. This is the minimum, and you can see that at maximum tau is 0, at minimum also tau is 0, and tau is maximum, sigma is not 0. But if the Mohr circle comes like this, that is the case of pure shear. If sigma x and sigma y, sigma x is plus 3 and sigma y compression is minus 3, center will be here. Now at tau max, sigma is also 0. So if girl is highest marks, tau highest, boyfriend may be there or may not be there. Here sigma is 0, sigma is boyfriend, and may be 0 or may not be 0. Okay. Now guys, whatever the expressions of sigma, the same expressions are for strain also, but only thing that instead of sigma you will be changing by epsilon, and instead of tau you will be changing gamma by 2. Like here epsilon x dash, epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 cos 2 theta, instead of tau represent gamma by 2 sin 2 theta. Similarly this also, like here gamma x dash y dash by 2 is equal to minus epsilon x y by 2 sin 2 theta plus gamma x y by 2 cos 2 theta. Okay, now their radius is with this. Okay, so here instead of tau it will be gamma by 2, instead of sigma it will be epsilon x. So whatever the expressions are in the stress for tau max, for everything, it will be for strain also. Instead of sigma just replace epsilon, and instead of tau replace gamma by 2. All things will be there. Like if you want epsilon 1 slash epsilon 2 principal strains, it will be epsilon x plus epsilon by 2 minus under root epsilon x minus epsilon by 2 whole square plus gamma xy by 2 whole square. Understood this? Give me yes or no. Understood this? Give me yes or no. Everyone? 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 Please let me know. Whatever the things are for stress. Hello sir. सर आप रेडी हैं? मैं कर दूं, स्टॉप कर दूं? हेलो, कर दूं ना? बस 2 मिनट में कर रहा हूँ, 2 मिनट में कर रहा हूँ. ओके ओके. So guys, whatever the things are for stress, na, the same thing will be for strain. Instead of sigma, you have to write epsilon. Okay, and one more thing. Tau max is either you can see radius, okay, this one, or it is sigma 1 minus sigma 2 is diameter, na? Sigma 1 minus sigma 2 is diameter, na? So it is sigma 1 minus sigma 2 by 2. That is for plane condition, for 2D condition. For plane condition. For absolute means 3D condition. In 3D there are 3 principal stresses. All these things are for 2D. 3D there are 3 principal stresses. In that case it is maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, comma sigma 3 minus sigma 1 by 2. I'm not going into writing because I know you have so many notes of formula. Okay. So guys, now Dheeraj sir will be coming. I will be going from the screen. Okay. And he will be taking the other parts. Okay. ये हो गया. कुछ डाउट होगा तो धीरज सर से पूछ लेना यार. Okay. Now Dheeraj sir will be taking all these things. Okay. And tomorrow is mock test. 26th is mock test. Civil and mechanical both. And I will be there for geotechnical prediction. I will be there. Okay. So now I will be going from the screen and soon Dheeraj sir, the super duper Dheeraj sir will be coming in the same screen. Okay. Super duper Dheeraj sir will be coming in the screen guys. So please share the video again with everyone. Okay. Thank you guys. Take care. Please let me know.
Yes, good evening guys to all of you. I feel you all have studied many topics now. Abhinav sir have just left you with a very wonderful lecture. Wonderful things sir have already given you. Now I will continue that and we will complete the session guys. Yes Shruth, good evening. Yes Sarath, Arun. अरे good night तो सोते हुए बोलते हैं ना. Hello Bhaumik. So guys, now I will be taking the left topics like deflection is there, like torsion is there, like spring is there, like column is there. So all those topics now I will be taking care of. So guys, don't worry. We are going to continue the game from here. Yes. Gaming with Nom. Good evening, bhai Ajay. Hello, dear. So guys, you know this is Formula 1 series going on and this is some detail about me. I'm having around 10 plus years of experience and this subject is related to strength of material. And guys, this is the Telegram channel. You must be a part of it. That is Mechanical by Dheeraj Sardana. There you will get the PDF of the session, PYQs and many more things. Now without wasting your time, we are starting the topic. So guys, first of all, we are talking about the torsion. You already have studied the bending equation, I feel so. So when you have already studied the bending equation, that was M upon INA is equals to sigma B upon Y is equals to E upon R. That you have already seen. That is the part of bending. You know that. And what was bending actually? When you were having a body like this and a couple was created, a couple was applied, that is having a plane perpendicular to the plane of cross section. Now my dear, if we are going to apply a couple, yes Arun, good evening. So when we are going to apply a couple that is having parallel to the plane of cross section. Okay Arun, that's fine. So guys, now we are going to apply a couple that is having plane parallel to the plane of couple. That kind of couple is said to be twisting couple. And guys, whenever a body is subjected to twisting couple, that condition is said to be the pure torsion. Generally, students are getting confused between rotation and torsion. So guys, if a body is rotated like this is rotation. But my dear, if we are keeping one end fixed and rotating other, then it is said to be torsion. So rotation we study in engineering mechanics and torsion we study in the strength of material. I will be having an animation also for the same. You can see this end is kept fixed here this end is kept fixed here, and then we are rotating the shaft. And when we are rotating the shaft, my dear, you can see this condition is said to be the torsion. So like we derive the bending equation, on the similar note we can go for the derivation of torsional equation also. So how we will be getting the torsional equation, that also we will see now. The torsional equation is given like this. This is T by J is equals to tau max divided by R is equals to G theta by L. I would also be like one more thing here, that is equals to tau upon R. So if you see this equation is very much similar. When you were applying the bending moment was acting about the neutral axis. So we were writing here I and A. Okay. And we are writing here J because this is acting about longitudinal axis. So J is nothing but I about longitudinal axis. So my dear, here maximum shear stress. Why? Because bending couple was creating the bending stresses, and my dear, shear stresses are coming because of twisting couple. So my dear, at maximum distance from neutral axis, we were getting the maximum bending stresses. At maximum distance from the center, we are getting maximum shear stresses. And at the same time, you were having here E divided by R. So here we have G theta by L. So in place of E, we have G. In place of 1 by R, we have theta by L. Because you must have seen, when we are having a kind of arc like this, you generally write R into theta to be L. So you write L is equals to R into theta. So 1 by R will be coming out to be, 1 by R will be coming out to be theta by L. This I am just telling you for remembrance purpose, that if you remember the bending equation very easily, you can remember torsional equation also. That is not a different thing. But what I have written here is, tau by small r also I have added, because sometimes they can ask you the question from this, like tau max by capital R and tau by small r. What do you mean by this? How the question will be framed? They will be saying, if we are having a shaft which is subjected to the pure torsion, and in that shaft the maximum stress induced is 100 MPa, that shaft is having a radius of 50 mm, then what would be the shear stress induced at a radius of 30 mm? So if they ask this type of question, generally student feels the data is not sufficient, because they have this how to find out the shear stress at some radius r. So if you will be equating them, my dear, you can find out the value of tau. From here you can take one more note point, that shear stress is directly proportional to r. What do you mean by that? If we are going to plot the shear stress distribution, you know shear means parallel to the cross section. Shear means parallel to the cross section. So if you are having a shaft like this, and you know that it is torque, then on this cross section you are applying the torque like this. To show the shear stress distribution, you will be just taking any diameter. Like I want to show the shear stress on this diameter. So you will be making this diameter. You will be making from center to radius perpendicular opposite to the twisting couple, then radius perpendicular opposite to the twisting couple, and variation is going to be linear because tau is directly proportional to r to the power 1. And guys, you will be making this distribution like this. But my dear, I would like to say that, like Abhinav sir have already told you the bending equation, there is one thing different in torsion and bending. That bending equation you have applied for I section, you applied for rectangular section, you applied for circular section, you applied for T section. For any section you can apply. But when we are talking about the pure torsion case, this equation we are going to apply for circular cross sections only. For different cross sections, you may not have the same distribution of stresses. That's why your chapter name is torsion of circular shaft. They are not normally writing torsion of beams, torsion of shafts. They write torsion of circular shaft. So my dear, you know, in circular cross section, we can have two types of things. One is solid circular, other is hollow circular. Okay, so you can have these two. So for both, my dear, we must be aware of the J means I about ZZ axis. Z means longitudinal axis. So my dear, if we want to write down the value of J, you know that by perpendicular axis theorem, if we have a shaft like this, then you must be aware of that there is one axis xx, other axis yy, third is zz. So by perpendicular axis theorem, what you can write, izz is nothing but ixx plus iyy. So my dear, when you will be writing ixx, it is going to be pi by 64 d ki power 4. This I am writing for solid shaft. Then pi by 64 d ki power 4. So my dear, you will be getting this to be pi by 32 d ki power 4. क्या सभी लोगों को समझ में आ गया? Everybody understood? Please tell me. Arun, yes, Ajay, Bhomik, Teju, Sardana. Yes. Tell me, guys, are you getting it properly? This is how we are using it. Shruth, very good. Yes, my dear. This J is also said to be the polar area moment of inertia. It is also said to be the polar area moment of inertia. And I feel everybody knows J tells us resistance to torsion. Yes, Ajruddin, welcome to the session. Yes, Arun, Bhaumik, bahut hi badhiya, Sarath. So guys, this is how the things are going to happen. Now, my dear, if you want to write down the power is given as torque into omega. Now, my dear, this is the torsional equation we have seen. Yes, Ishaq, hi dear. Balaraj, hi dear. So let us move further, guys. So this is one information that we are having a production engineering formula series also. So those who are looking for the topics which have not been covered till now, like metal forming and all, I will be taking all those topics in that session. So be ready for that. This was just for your information. Yes. So my dear, now I would like to tell you one very important thing, that you have written the equation T by J is equals to tau max divided by R. So if you want to find out the maximum value of shear stress, you can use this part of the equation. So from here, what we can write, tau max is equals to T into R divided by J. So you can also write it as T divided by J by R. And this J by R is said to be polar section modulus. It is written as T by ZP, where ZP is defined as J by R. Here R should always be the maximum radius. Always remember that. And what is the name of ZP? Shruth, actually it is planned tomorrow. Most probably it is going to be on Thursday, means 26 January, tomorrow. I feel 10:30 would be the time. Okay. So rest you will also be getting the information on my Telegram channel also. But tomorrow is that. Okay. Tomorrow we have mock test also in the morning, and in the evening I will be taking that. So guys, the ZP is J divided by R. R is the maximum radius. Yes. So now it comes to shear modulus. G is shear modulus. Balaraj, shear modulus is G. When we are talking about shear modulus, it is G. Okay. Modulus of rigidity. When we are talking about ZP is the polar section modulus. Polar section modulus. And my dear, if you see ZP, you can write tau maximum is inversely proportional to ZP. So if ZP is more, tau max will be less. So my dear, if ZP is going to be more, the shear stress induced are going to be lesser. What do you mean by that? It means, yes, polar section modulus. It means this ZP is somewhere giving us the strength of shaft. It is giving us the strength of shaft. So my dear, if we are going to use this part of analysis, we can go for a comparison of solid shaft and hollow shaft. If I ask you that solid shaft versus hollow shaft, which shafts are going to be better? Solid shafts are better or hollow shafts are better? Solid shafts are better or hollow shafts are better? क्या बोलेंगे सभी लोग? क्या solid अच्छे होते हैं या hollow अच्छे होते हैं? Solid shafts are better or hollow shafts are better? What you will say, guys? Solid are better or hollow are better? What will you say? Solid are better or hollow are better? Ramesh Mohan is saying, sir, hollow are better. Vineet is saying, sir, depending on condition. Yes, it depends on condition. So my dear, if we have radial space to be constrained, means if we have the same diameter for solid and hollow shaft, both shafts are made up of same material, they have same outer diameter, they are running at same speed, they are made up of same material. Under these conditions, solid shafts are said to be the better ones. And under this condition, if you find out the ratio of power transmission capacity to the solid shaft to the hollow shaft as 1 minus k ka square, sorry, 1 minus k ki power 4. This is the formula for that. Okay, where what is k? If the diameter of hollow shaft, inner diameter is di and outer diameter is d naught, then my dear, this ratio of di by d naught is said to be k. So guys, this is the ratio of power transmission capacity for a solid to the hollow shaft if we are talking about the condition of radial space to be constrained. If we are having same radius for both of them, same outer radius for both of them, then this formula you can apply to compare the power transmission capacity. Is it clear for everyone? And guys, before we go to the shear center, I would also like to tell you one more point. Here. Okay, I would also like to tell you one more point here. Yes, fine guys, let us see what is that. Just give me a second. Fine. Okay, moving further guys, let us move. So guys, if I say that we are having solid versus hollow shaft, where solid shaft and hollow shaft, just wait. Yes, I feel it was hanging. Okay, no issues. So my dear, if we are going to have a comparison of solid shaft and hollow shaft in such a way that their weights are equal, if we are going to have the weight of solid and hollow shafts are equal, so my dear, if equal weights we are talking about, for such cases, hollow shaft will always be bigger in size, because you know some material is being removed from that. And if you are going to compare a solid and hollow shaft in such a way that they are having equal weights, then every time you will be having bigger size of the hollow shaft. And for that case, if you are going to have a comparison of power of solid to the power of hollow shaft, you will be getting 1 plus k ka square divided by square root of 1 minus k ka square. So my dear, this is the formula going to be for power of solid to the power of hollow. Once again, you know, k is defined as inner diameter to the outer diameter ratio. Sir, XCK PYQ question है आपके, हाँ विनीत, I will share you with that. Okay, मैं share कर दूंगा आपके साथ. So guys, this is about the twisting couple. It is about the solid and hollow shaft. Let us see one more thing. You know, T by J can be written as G theta by L also. From here you can find out the angle of twist to be TL by GJ. So from here you can find out the angle of twist to be TL by GJ. And just like you have studied the bars in series, bars in parallel, similarly you can go for shafts in series. So when you will be having the shafts in series, my dear, then for shafts in series, you will be writing theta total to be equals to theta 1 plus theta 2 plus theta 3. And similarly, when you are going to have the parallel connection, for parallel connection, you will be having theta 1 is equals to theta 2. So guys, this is how we will be using, similar to the bars in series, similar to the bars in parallel, there is no difference. तो हम उसी की बात करेंगे. So guys, if radial space are constrained, solid shafts are better. But if weights are equal, then hollow shafts are better. So for different condition, we have different shaft to be better. This ratio will also be equals to the torque of solid to the torque of hollow. Why? Because they are running at same speed, they are having same material. So that is why omega will get cancelled out. So this is about the torsion, my dear. And we have also seen the formula for angle of twist. You can also define torsional stiffness is equals to that is T divided by theta, which will be coming out to be GJ by L. It is similar to the axial stiffness. So this is the formula for the torsional stiffness. I feel everybody would be getting it. So guys, do like and share the session. Now we are moving further to the next topic, which is shear center, springs and column, that we will discuss. Okay. So my dear, first of all, we will talk about shear center. then we will enter into the deflection, and after that we will enter into the column and spring, and in that way we are going to cover it. So please tell me everybody is getting everything. We have seen the torsion formulas. Okay, and I will be also covering one interview question in between for your understanding purpose. I will tell you one more thing. So first of all, let us talk about the shear center. So you must be aware of that what is shear center. It is a topic newly added, very small topic it is. So when we are talking about the shear center is a point. It is said to be a point at which if the entire shear force is going to act, it will not be creating any kind of twisting moment. So many students, what they feel is that if we are going to have a body like this, then my dear, everybody feel it that if the shear force is going to pass from a point other than centroid, it will be creating the twisting moment for sure. So generally student feels like that it will be creating a twisting moment. So they feel that this centroid point is the shear center. So I would like to say, guys, shear center is generally defined for the open section like I section, plus section, T section, L section, C section. So for such section, shear center is generally defined. So my dear, when we are talking about these open section, so there are a lot of calculation involved in the determination of the position of shear center. But for GATE, whatever the objective questions we are getting, this is going to be slightly different. Okay. Before we go further, I would like to tell you guys, on this channel, when you are going to give the GATE examination for mechanical, civil, both the branches, or XC also. So when you are going to appear for the mechanical paper, just after your exam, we will be live on this channel, and we will be going for the analysis of the paper, where we will also go for the solutions of the question. So don't forget to come with us on this channel just after your exam. So as you come out from the examination hall, do join us for the live session. Be ready for that. Okay. Now, my dear, we are talking about how to find out the shear center. So my dear, for objective paper, you need not to derive all those relations, because they need 2 to 3 pages of derivation. For that, I would be giving you a shortcut how to find out the shear center. So my dear, first of all, you will see any cross section what is given to you. Is it symmetrical about any axis? Like if you see this I section is symmetrical about x axis. So if it is symmetrical about x axis, it means shear center will lie on that axis. Similarly, if I ask you, is it symmetrical about y axis, then shear center will lie at y axis also. So my dear, if shear center we need to find out, you are saying for I section it is symmetrical about x and y axis. So shear center will lie on x axis also, y axis also. So shear center will be lying on the intersection of them. So this point will be acting as shear center. Then my dear, we are having plus section. If you see this also, it is also symmetrical about x, symmetrical about y. So you will say here the shear center will be lying. But my dear, there are some section like L and T, they are not symmetrical about both the axes. Like if you see this section, it is not symmetrical about x and y both. So for such cases, we have rule number 2. If you can feel a section to be made up of 2 thin rectangles, then my dear, you can find out the shear center on their intersection. Like if you see this L section can be thought like it is made up of 2 thin rectangles. So if you can feel it, definitely here will be the intersection. So this point will be acting like a shear center. If you are talking about T section, you can feel that this is one rectangle, this is other rectangle. So my dear, shear center will be lying on this point. This is going to be shear center. Is it clear? So you need to apply these 2 rules, because for you guys, question will be coming from this type of rules. Like in civil engineering, this L section have already asked 2 times. And if we are talking about the mechanical engineering, this is the first time it was added in 2021. Till now, there is no question. Okay. Not very important topic, but we have discussed it. Okay. So now we will be entering into the next topic, that is deflection of beams. Okay. So when we are talking about the deflection of beams, I feel everybody remember, when we are having a member like this, then when you call it beam, when it is subjected to some shear forces and bending moment. When any member is subjected to shear forces and bending moment, we call it as beam. You know that. So my dear, if it is subjected to shear forces and bending moment, under that it is going to deviate. Under that it is going to deviate like this. So if you see this deviation is happening in two ways. One is it is deviated from longitudinal axis in lateral direction. So my dear, this lateral deviation of the beam from its longitudinal axis is said to be deflection. And similarly, if you see, it is making some angle with x-axis. So this angular deviation with respect to longitudinal axis is said to be slope. Yes, Bablu Saha, good evening dear. So this is said to be the slope. So angular deviation is slope and lateral deviation is deflection. So if that is the case, when we are talking about slope and deflection, these both are going to help us in designing the beam based upon rigidity criteria. Like when we find out maximum shear force, maximum bending moment from SFD BMD, that helps us in designing the beam based upon strength criteria. Similarly, slope and deflection helps us in designing the beam based upon rigidity criteria. So my dear, when we are going to find out the slope and deflection, our interest is to find out the maximum slope and maximum deflection in this chapter. This is the target of ours. So my dear, you must have seen there are many methods you have seen. First method you have studied as double integration, then Macaulay method, then principle of superposition, then Mohr moment area method. Then you have also studied strain energy method. Then you also studied some other methods like Maxwell reciprocal theorem. So guys, for all those methods to apply, you remember the most important is principle of superposition, which is coming generally every time in the exam. And for that you need to remember some basic cases, because what principle of superposition says? Principle of superposition says, if we are having a beam like this, and on this one force is acting, one moment is acting. So there are two loads which are acting. So if more than one load is acting on a beam and you want to find out the deflection of this point A, then deflection of point A will be written as deflection of point A because of load plus deflection of point A because of the moment. So you will be adding their individual effects. That is what the deflection is going to be find out. And my dear, this is how we are using the principle of superposition. So what it says, if you have more than one load, then the total deflection will be coming because of both. So algebraic sum of their individual effect is going to be your answer. So first of all, we will imagine only P is acting, then we will imagine only M is acting, and we will just add them. But my dear, to apply this principle of superposition, we need to know the values. What would be deflection because of load P? What would be deflection because of moment M? So my dear, here is the table, which if you are going to remember, you are very easily going to solve the questions. And if you are not going to remember, then you have to apply some of the method to find out these values. Both of them are okay methods, good method. But as here we are discussing formulas only, so I will be showing you the formulas for that. Sir, is principle of superposition? Dear, actually, when we are talking about all the methods for non-prismatic beams, we are having Mohr method. All other methods, when we see double integration, Macaulay, they are applicable on the prismatic. And when we are talking about the Mohr's method, both the method, whether it is conjugate beam or moment area, they are applicable for non-prismatic beams. Okay. So my dear, now let us discuss about this. So when we are talking about this moment, if point moment is acting, then slope will be ml upon ei, deflection will be ml square upon 2ei. So when we are talking about this is only magnitude. Direction I have not considered, because it is understood that it will be deflecting like this. So deflection is going to be downward and slope is going to be clockwise. So my dear, generally when we are talking about the sign convention, then my dear, we are going for the first quadrant positive. First quadrant positive means deflection in upward will be positive, deflection in downward will be negative. Then slope in clockwise will be negative and slope in anti-clockwise will be positive. We are going with this sign convention. Otherwise, you can go for opposite also. That will be your choice. But for that, you need to use different equation. Like for my sign convention, equation is EI d square y by dx square is equals to mxx. If you are using opposite to that, you need to consider a minus sign here. So for this convention, this is the equation which we are going to follow. Yes. Yes, Ajay, don't worry. We are going to see that. Don't worry. Yes, Ajruddin, there are 8 to 9 cases for principle of superposition, but here we are discussing only the formula. Whenever, if you see the marathon session when we have taken, there we have covered all the cases also, but here we will see only formulas. So for this point moment, this is the formula. When we have point force, then my dear, slope is WL square by 2 EI, deflection is WL cube upon 3 EI. Okay. If you find any difficulty, any doubt, you can ask me. Then my dear, if we are going to have UDL, W kilonewton per meter, then slope will be WL cube by 6 EI, deflection will be WL4 upon 8 EI. Similarly, my dear, if we have UVL, this UVL is having zero load at the free end and W load at the fixed end. So for this, if you see the formula, it is WL cube by 24 EI and WL4 by 30 EI. So you just need to remember these coefficient, then you will be able to answer it very easily. If you are having simply supported beam subjected to the point moments, then slope at A and B will be ML upon 2 EI and deflection will be ML square upon 8 EI. Then my dear, if you have point force on simply supported beam, then it is PL square upon 16 EI is the slope, Y maximum is PL cube upon 48 EI. Then my dear, for UDL we have WL cube by 24 EI. Is it 24 EI or something different? Then it is going to be 5 by 384 WL4 by EI. So guys, I would like to tell you, up to UDL you shall remember. For this type of loading, chances are not there that they will ask you. So you need to remember up to UDL, okay, at the max up to UVL on cantilever. That is fine, okay, not more than that is required. This type of cases have no chance to come. Still, I have kept it. If you want to remember it, you can remember it. Okay. Then my dear, moving to the next case, case number 9 and 10, that is for the fixed beams. You know, for the fixed beams, it will be deviating like this. So that is for sure. Slope at A and slope at B are going to be 0. There is no problem in that. Okay. So I feel everybody got it about this. So these are the 10 formulas which you need to remember. So guys, we have already discussed the sign convention. So with the sign convention, you need to do the things. Here I would like to tell you one more thing about principle of superposition. Like whenever you are having this beam and you are saying that you are having a load like this. Okay, this is the load and this is the moment. In such case, you can see P is doing the deviation or deflection downward, moment is doing upward. Then how you will use it? You will say Y at A is equals to Y at A is equals to Y at A because of P plus Y at A because of M. You know, because of P is downward, so minus PL cube upon 3 EI, and then you have plus ML square upon 2 EI. So you need to take care of sign convention also. And guys, this is the principle of superposition. Now I would like to tell you the Maxwell reciprocal theorem also. Maxwell reciprocal theorem, when we are going to use, if we are given a beam, like that, this is a beam, and on this beam we are given 2 points. This is point A, this is point B. So if on the same beam they are saying consider 2 points, and they are saying if we are having load at A, if we are having load at A to be equals to 2W, let us say, and they are saying deflection at B due to load at A, that is given to you as delta. Then they will be saying, what if we are going to apply a load of 3W at B, then what would be deflection at A due to load at B? So you know, if load will be acting at A, then also deflection will be happening at B, and if load is acting at B, then also deflection will be happening at A. So if load at A is 2W, deflection at B due to A is delta, and load at B is 3W, then what would be the deflection at A due to load at B? So my dear, if such question is coming, you need to use the Maxwell reciprocal theorem, which says that WA into YAB is equals to WB into YBA. Guys, do like and share the session. We are covering each and every minute thing which can help you in the examination. So don't worry about that. Ajruddin, I feel you got it. We are not going for all the cases that we have already seen in the marathon session. Here we are just revising the formulas. Is it clear, Ajay? So I am coming on to strain energy also. So this is Maxwell reciprocal theorem. Now, my dear, I am talking about the strain energy. When we are talking about the strain energy method, then strain energy method says partial differentiation of total strain energy with respect to moment will give you the slope, and partial differentiation of strain energy with respect to force will give you the deflection. So this is how the strain energy method can be used. But the problem with the strain energy method, that when you will be finding out this deflection or this slope, yes, Arun, are you also getting or not? Arun, Bablu, Sarath, yes. So guys, when we are talking about this slope and this deflection, they will be the slope and deflection of that point on which load is actually acting. So my dear, if I am having a cantilever beam and I am saying some load is acting at this point, that P load is acting at point A, P load is acting at that point A. So whatever the deflection or slope you will find out, that is for that point only. Similarly, if we are having a simply supported beam, let us say, and my dear, you are using the strain energy method and I am saying load is acting at this point. So my dear, when you will be doing this, you will be getting the strain energy, you will be getting the deflection at the point at which the load is acting. So for that point is very, very important when you are applying this strain energy method directly. So I feel you are getting it properly. Is it clear for everyone? I feel you are getting it properly. Yes. So we are moving further, guys. So this is about the strain energy method. Now, my dear, whenever we are talking about the moment area method. So moment area method also have a formula. That is, whenever you want to find out the slope at B minus slope at A, that is given by 1 upon EI area of bending moment diagram between A and B. This is the formula for slope for prismatic beams, because in prismatic beams EI is going to be constant, and if we are going for non-prismatic beams, you will be writing theta B minus theta A is equals to area of, here you will be having M upon EI diagram, between A and B. So guys, in formula revision we are revising the formulas. In the practice, we will do practice of these questions also. So guys, tomorrow you both the branches have mock test also for mechanical and civil. Do come live there also. We will see some questions on these things, so you would be getting everything properly. And on this Sunday or Monday, we are also planning MSQ session for you guys, so be ready for that also. We'll be coming with more than 50 MSQ for entire branch, so be ready for that also. Okay, you are going to get a lot before your exam, guys. So we have seen this for slope and deflection. When you will find out the deflection, then deflection at a point, let us say we are having a cantilever beam like this, and whatever be the loading we are having, this is A, this is B. So my dear, you can write deflection at A to be equals to deflection at B plus slope at B into AB plus deflection at A with respect to tangent at B. So when you are finding out this thing is given by moment of area of M upon EI diagram between A and B. You are finding out deflection at A, so I will say about A. So my dear, this is about the formula for moment area method. I feel everybody would be getting this formula. This is just for a revision purpose. So guys, if you have any difficulty in this, in the practice session as well as in the mock test, we are going to have 1 to 2 questions from that also. So be ready for that. Now we are entering into the next topic, that is the pressure vessels. So now we will be talking about the pressure vessels. So my dear, like you have LPG cylinder in your home, that is having some LPG gas, you know that, liquid petroleum gas. So those cylinders, they are counted as the pressure vessels. Pressure vessels are those who are carrying the liquid or gas, because both are going to produce some pressure. And my dear, they can be of two types, thin or thick. We can have pressure vessel of two types. One is said to be thin, one is said to be thick. In the ESC paper, many times they have also asked what is the criteria for thin and thick. So my dear, if D by T ratio is more than or equals to 20, D is diameter, T is thickness. If D by T ratio is going to be more than 20, we call it as thin. And if D by T ratio is coming out to be less than or equals to 15, we call it as thick. In between, my dear, we cannot say exactly, that will be depending on the conditions. So my dear, when we have the thin cylinders, then for thin cylinders, I will be showing you three types of stresses actually. So my dear, this is a cylinder. As I am saying, this is a thin cylinder. So I will be making the thickness also. So this is the thin cylinder. Then my dear, first of all, I would like to tell you, if any fluid, any gas, any liquid is there, then my dear, that will be inducing some pressure onto the walls. And because of this pressure, my dear, there will be a tendency of increase in the circumference. So my dear, always in the circumference, some tensile stresses will be induced, and those stresses will be having a tendency to increase its circumference. And that is why these stresses are said to be the circumferential stresses. They are said to be circumferential stresses. And my dear, the formula for this circumferential stresses is given as that hoop stress is sigma h is equals to PD by 2T, or you can write it as PR by T. Both are correct formulas. Now my dear, you also will be having a stress in the longitudinal direction. But when will it come? When, my dear, if you are having at least one end to be closed. So if one end will be closed, pressure will be acting on this also. So because of this pressure, my dear, some stresses, some tensile stresses will induce in the length also. So my dear, those stresses are said to be the longitudinal stresses, and longitudinal stresses are given as PD by 4T. In other words, they are hoop stress divided by 2. So longitudinal stresses are hoop stress divided by 2. Now my dear, you already know that whenever we are talking about the thin cylinders, for thin cylinders, we know that if we want to write the circumferential strain, it is sigma C by E minus mu times sigma longitudinal by E. Because you may be thinking, sir, have we missed one stress? Because stress should be three types. We have taken longitudinal, we have taken circumferential, but my dear, we have not considered the radial stresses. Why? Because this dimension is very, very small. That is why we are assuming the stresses in this dimension to be 0. When we are assuming stresses in this dimension to be 0, this is a plane stress condition. That is why we are considering radial stresses to be 0 for thin pressure vessels. And as you are considering only two types of stresses, that is why if even you write minus mu times sigma R by E, you know radial stress is 0. That's why this will not affect, and this will be the formula for circumferential strain. And when you will be putting the value of sigma C and sigma longitudinal, you will be getting the hoop strain to be PD by 4TE into 2 minus mu. Similarly, if you want to find out the longitudinal strain, my dear, then longitudinal strain will be sigma L upon E minus mu times sigma C upon E. And once again, you can write minus mu times sigma R upon E. You know sigma R is going to be 0. So my dear, once again, this will be your formula. And when you will be putting the value, once again, you will be getting the formula for longitudinal strain as PD by 4TE into 1 minus 2 mu. So my dear, sometime they can ask you the ratio of circumferential stress to the longitudinal stress. You will be having the answer to be 1. Sometime they can ask you the ratio of circumferential stress to the longitudinal stress. You will be writing it to be 2 minus mu divided by 1 minus 2 mu. So knowing the value of Poisson ratio, you can find out the ratio. Now my dear, we will be entering into one more strain, that is said to be the volumetric strain. You know that it is 2 times the circumferential plus the longitudinal. When you will be finding it out, you will be getting it to be PD by 4TE into 5 minus 4 times of mu. This is going to be the volumetric strain in the thin cylinder case. I will also like to add one more thing. You can see this volumetric strain. One more thing I would like to say, if they ask the strain in the third dimension, radial strain, that will not be zero, because in plane stress condition we can say stress is zero. For strain we cannot take any such guarantee. So for epsilon r, what you will be writing? You will be writing sigma r by E minus mu times sigma c by E minus mu times sigma L by E. And you won't believe, in GATE 2022 question is from this in mechanical paper. So in mechanical paper, this was the question, that what is the change of thickness. So you know, in the radial strain you will be having change in thickness per unit thickness. So you can find out the change of thickness using this formula. I feel everybody is getting it. This is something related to the thin cylinders, and now we will be moving to the thin spheres. Okay, is it clear? Yes. Moving further, when we are talking about the thin sphere, then my dear, you know that in the thin cylinder we were having the state of stress like this. In thin cylinder we were having the state of stress like this, sigma circumferential, sigma longitudinal, like this we were having. Okay, but my dear, when we are talking about the sphere, in the sphere, as sphere is same along all the directions, so if you are going to make the state of stress in the sphere, it will be coming out to be everywhere sigma, sigma, sigma. This is the case where Mohr circle is becoming the point. So for this case, Mohr circle is going to be the point. If Mohr circle is point, shear stresses are going to be zero, and my dear, normal stress will be coming out to be same, which is sigma circumferential. And for thin sphere, when you will be finding out the circumferential stress, hoop stress, there is nothing like longitudinal here, only hoop stress is there, that is PD by 4T. Similarly, if you will find out hoop strain, there is nothing like longitudinal, that is PD by 4T E1 minus mu. And volumetric strain will be 3PD by 4T E1 minus mu. If you want to find out the shear stress, then for shear stress you can use tau maximum to be equals to, this is sigma circumferential. Okay, I am saying the formula you already know. If you know the principal stresses, then you know it is sigma 1 minus sigma 2 by 2. Okay, this is the formula for in plane maximum shear stress. In plane maximum shear stress. And if you are going to consider 3-dimension case and taking sigma 3 to be 0, then you can write the absolute tau max also. So in the question they can ask you absolute or in plane. There you will write maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 1 minus sigma 3 by 2. Putting sigma 3 to be 0, you will get the answer. I feel everybody is getting Rishabh sir, maximum shear stress we have to dear, yes, if they will be asking the maximum shear stress in the wall of cylinder, you will find out the absolute one. Okay, so let us move further, guys. I feel everybody got it. Everybody got it. Shall we move on now? Yes. Then my dear, thick cylinder otherwise are not coming in the paper, neither they are mentioned in the GATE syllabus, but still I am going to give you some glimpse of that. So my dear, here this is the 3-dimensional state of stresses where circumferential, longitudinal and radial, all stresses will be coming into the picture. And for this the formula is given by Lamb's equation. Hoop stress is given as sigma xx as b by x square plus a tensile. Radial stress is b by x square minus a. Plus means tensile, minus means compressive. A and b are the Lamb's constant. Just remember the equation, nothing more than that is required here. Okay guys, yes. Then my dear, analysis of thick spheres, you will be having this formula for that. Okay, so this is 2b by x cube plus a tensile. 2b by x cube, this minus means compressive, plus means tensile. So you know sphere is having all the dimension to be same. So that is why in the sphere we are having no circumferential longitudinal, it is only circumferential. Okay, so I feel you got it. Moving further guys, now it is the time for column. I feel everybody got for pressure vessels. Now let us talk about the columns. So my dear, when we are talking about the columns, you know that there are 3 types of column. One is short column, medium column and long column. We are having 3 types of column. One is short column, other is medium column, and third is long column. You know, my dear, short column is getting failed due to crushing, and long column is getting failed due to buckling. Long column fail because of buckling, short column fails because of crushing. Medium column can fail by both crush or buckle. So for long column, Euler have given the theory, that is given the name of Euler theory for long column. And according to that theory, buckling load is given as pi square EI minimum divided by LE ka square. Sometime you can also write it as n square pi square EI minimum upon LE ka square. So my dear, I feel you know LE is the effective or equivalent length, and when we are going to define LE for different end condition. So my dear, when both end are hinge, both end hinge means like this. For this condition, LE is equals to the length. If nothing is mentioned, you will use this relation only. Then my dear, one end fix, other is free. One end fix, other is free. For this case, it is 2 times of L. For both end fix, it is going to be L by 2. For one end fix and other hand hinge, it is going to be L by root 2. Okay. So these are the formulas you would be using. B1, if we are considering the buckling to be like this. If we are considering the buckling to be like this or this. And if we are going to have like this, then n is equals to 2. When we are saying n is equals to 2, you can understand that buckling load will become 4 times. Is it clear? So that kind of thing can be asked in the paper. Till now they have never asked, but they can ask you. Then my dear, we are going to discuss the springs. In the column, I would also like to tell you one more thing as core. You know, core is that region in which if load is applied, there will not be any tension in the component. Ajay, I am giving you, but in the syllabus only Euler's theory is mentioned. But if still you want to apply the Rankine, then Rankine say 1 upon PR is equals to 1 upon PE plus 1 upon PC. You can directly use this formula rather than going for the derivation. PE you already know, that is pi square EI minimum upon LE ka square. And PC is sigma CR into area. There is one more thing, that is slenderness ratio, which is defined as LE by K minimum. Here K is the radius of gyration. S is the slenderness ratio. So K minimum is given as square root of I upon A minimum. Here we are only looking at the formulas. In the marathon session, we explained each and everything in detail. I feel everybody is getting it. So this is about the Rankine formula. When we are talking about the core is the region of the column. Like if we have a rectangular column, then my dear, if you are going to ask about a region in which if load is applied, there shall not be any tension in the column. If you are asking the region in which if load is applied, there is no tension in the column, then my dear, that region is given like this. And if you see this region will be, you know that this is going to be B by 3, this is going to be D by 3. So this is said to be middle 1/3 rule. Okay, similarly, if you are talking about a circular cross section, then core will be coming out to be 1 by 4. This is 1 by 4 or D by 4. So that is said to be, it is middle 1/4 rule. Okay. Now my dear, you know, when we are talking about the springs, there are some formula related to springs also. I have given you all the formula. So in your syllabus, you need to take care of helical springs only. Although in the books, formulas are given for, you can say, other types of springs also. So when we are talking about the helical springs, my dear, helical springs under compression, N is the number of turns here we are talking about. You can see the strain energy will be given like this. U is equals to 32 P square R cube into N divided by GD ki power 4. Here D is the wire dia and R is the radius of coil. I feel you understand what is coil radius. So my dear, wire diameter is this. And if you see the central axis, then this is the radius of the coil. And we are talking about the mean radius. Like if you take this to this is the outer diameter. If you take inner to inner, it is the inner diameter. So this radius, we are defining it from center. It means we are saying this radius is d by 2, where d is d naught plus di by 2. Inner diameter of coil, outer diameter of coil, d is the mean diameter of coil. I feel everybody got it. I feel everybody's got it. Yes. Ajay, are you getting it? Ajay, Sarath, Rishabh Pant, Arun, all other student. Yes, Bhaskar, sir, can we mark 0 for core of the section? E is equals to 0. Dear, when eccentricity is 0, then so definitely there is no tension. But when we are talking about the core, it is about the eccentricity which is allowed without any tension. Because when load is eccentric, then only tension will be coming. Because that load, when it will become eccentric, it will create some kind of bending. That is the reason. Sir, for PE in denominator 1 plus A, so something like a formula. That's why I asked. I didn't get, Ajay, what you are saying. If you share it with me on WhatsApp, I can better clarify you. So my dear, now we are talking about the series connection. In series, we are going to add the spring stiffness like this, and in parallel, we are going to add it like this. Then my dear, sometimes they can give you about cutting of a spring. They can say we are having a spring whose stiffness is K, and we are going to divide it into two unequal part, M is to N. Then my dear, what would be the stiffness of upper part and lower part? Then for upper part, stiffness will be M plus N divided by M into S, or K you can say. For lower part, the stiffness will be M plus N divided by N into K. Similarly, if you are having a spring and you are going to cut it into three parts in the ratio of M is to N is to P, initial stiffness was S, then this part will be having a stiffness of M plus N plus P divided by M into S. Similarly, this part will be having M plus N plus P divided by N into S. Last part will be having M plus N plus P divided by P into S. So this is how the stiffness we can find out when we are going to have cutting of a spring. Very good, Ajruddin, बहुत ही बढ़िया. Tau max is given as 16 PR by pi d cube or 8 PD by pi d cube. If you are writing in terms of diameter, strain energy stored in spring is T square L upon 2Gj or 32 P square R cube N upon GD की power 4. Then you know deflection will be nothing but del U by del P. That is 64 PR cube upon GD की power 4. Then my dear, what is coefficient of stiffness of spring? That is K. P by delta. That is defined as GD की power 4 by 64 R cube N. You can see stiffness is inversely proportional to N. That is why when we were having cutting of spring, we have kept this M in the denominator, this N in the denominator. That is the reason, because stiffness is inversely proportional to length. Okay guys, this is how we are moving ahead. Then my dear, there is one more thing. You can see the actual, okay, buckling load we have already seen, I feel so. Then my dear, that also I told you which column fails under which type of stresses. Conditions also we have discussed. Now I am going to tell you about strain energy. Arun, याद नहीं होता है तो you can go with derivation also. If you see the derivation, they are also very easy. Like what you are doing there. If you see once the derivation, we are taking the effect of direct shear and twisting moment. Then we are adding it. Okay. So if you see the derivation, that is easier to remember. And I also do not remember the result, to be frank. I always used to derive it. Okay. So that is always going to be beneficial. If you want, at the end, I can show you some derivations if you want, if you have not seen before. Okay. Let us move further, guys. So guys, now I am telling you about strain energy and impact loading. The last part I feel which you are looking for, because there also some formulas are there. So my dear, when we are going to see the strain energy for different loading, we have different types of formulas. Like if we are going to have axial loading like this, if you're going to have axial loading like this, then strain energy is given as the integration of pxx square dx upon 2ea. Okay. If similarly we are going to have a member which is subjected to direct shear force, then my dear, you will be having strain energy to be vxx square dx upon 2g as. As is the shear area. As is the shear area. You can also write it as sigma square upon 2e into volume. You can also write it as tau square into 2g into volume. Similarly, my dear, if we are going to have a member under bending, then my dear, for that strain energy will be given as integration mxx square dx upon 2ei. Okay. And similarly, if we are going to have a shaft under torsion, for that you can write down the strain energy as half into t into theta, or you can write it as t square L upon 2gj. Okay. Or you can write it as integration txx square dx upon 2gj. Or you can write it as tau max ka square upon 4g into volume. Here there is a confusion because of direct shear, it is 2g. Because of torsional twisting moment by 4g. This is very, very important fact, guys. Always remember about this. Okay. I feel these are very easy to remember what I have shown you. You can also have hydrostatic state of stress. If you are having the hydrostatic state of stress like this, everywhere equal stress is coming, sigma p, sigma p, sigma p. Then my dear, strain energy will be given as sigma p square upon 2 times of bulk modulus into volume. Okay. So my dear, this is how strain energy formulas are there. Then we have impact loading. Impact stress is static stress into impact factor. Then impact elongation is static elongation into impact factor. Then you also know what is impact factor. It is 1 plus 2h by delta static. What is delta static? It is PL upon AE. Okay. So I feel every formula is covered now. Now please remind me if I am forgetting any formula. I will write that also for you. Yes, how this equation is coming. How this equation is coming. That is coming W into H plus delta I is equals to sigma I square upon 2E into volume. Sometime we need to use directly this formula also. So don't forget about this. Okay. I feel everything is covered now. We have seen deflection, strain energy, impact loading, thermal already sir have covered, simple stresses covered, HFDB, MD covered, columns covered. Okay, so I feel now we have covered all the things. If you find anything which we are missing, just make me remember I am here right now. तो पूरा करके ही जाएंगे, अगर कुछ है तो बताइए, ठीक है? So guys, one more thing I would like to tell you that whenever we are going to have the torsion, then you are applying the twisting moment like this. You know that if we are talking about a fiber like this which is rotating like this, and you know this is the fix, so I will be making like this. This is said to be angle of twist, this is said to be shear angle. Then you must be aware that theta is not at all a function of radius. Similarly, phi is not at all a function of length. Means if you change the radius, theta will not change. If you change the length, phi will not change. But theta is found to be a function of length. Similarly, phi is found to be a function of radius. These are how the things are varying. That can also be asked. Column में tension and compression. Dear, that core part is not required actually for the derivation, but I am telling you how the things are going to happen. Like if this is a column, this is a circular column, and my dear, this is your axis. If you are going to apply a force along the longitudinal axis, then there is no issue. But if you are applying the load somewhere eccentric, which is making at a distance of E, then my dear, you need to see the equivalent effect there. How you will see the equivalent effect? You will apply one load in downward direction, other in upward direction. This will be making a couple like this. So you can see this couple is coming here compressive, here tensile. So my dear, this will be creating tension in these fibers, compression in these fibers. So if you see the effect of this force, then due to this force, compressive stresses will be coming like this. This is simple P by A. This is simple P by A. But if you see the effect of bending, then effect of bending, here it is tensile like this. Here it is compressive like this. So these are the stress distribution because of the couple. So because of this tension, if this is more than this compression, these fiber will come in tension, and that is what we need to avoid. And that is the funda of core, kern and kernel. Core is having three names: core, kern or kernel. So guys, definitely you guys are getting benefited by different flavors. Like last year, some portion Abhinav sir have covered, some I have covered. This time we have somewhere differentiated. So definitely you got some extra things also, like Abhinav sir have taken a wonderful session. I have seen also. I was there at that time in my paid course class, but I was looking at the kind of response you have shown. So guys, thanks for your love and support. And guys, you must be having one question in your mind, that how to proceed with your last week, because the most crucial week of your preparation is the last week. Okay, so when the most important week is last week, because whatever you have done in the entire year, if you are not going to work properly in the last week, that entire will go into vain. So my dear, me and Abhinav sir would be coming on this Saturday to tell you how to utilize your last week, whether you shall go for numericals or you shall go for theory. So my dear, in those 7 days, what should be your strategy? What should you do to get the optimum or maximum marks? What should you do so that you can get maximum out of it? For that, me and Abhinav sir would be coming on Saturday. And this session is not like that I am saying any general things. We will be telling you the things based on the research point of view, which are already proven, will help you. So for that, we are also doing a lot of research for you guys. So be ready for that session. Okay. Dear, to find the load, the things are going to be same. Like if we have a taper bar, na Ajruddin, if you have a taper bar, so whether you take section here or here, there is no problem. To find out the force, you can take section anywhere. To this left hand side load P is there. So about this section load is P only. So there is no problem in taper bar or such type of bar. Force is calculated in the same way only. If something is going to change, that is the stresses, because area is different at every point. Force will be same, stresses will be different. Stress will be maximum here, minimum here. Is it clear, Ajruddin? Ajay, sir, I have another doubt. When we have moment in beam in somewhere between two ends, how to take limit in strain energy integral, sir? I feel you are asking about this. If you are having, let us say this is the beam, and you are talking about moment if you are having like this, then there is no problem, na my dear. You are always taking the strain energy. You will be dividing the beam into parts like A to C. You will be having this part as 1, this part as 2. You will find out the strain energy of 1, strain energy of 2. For strain energy of 1, you will be defining different bending moment, M11 square dx upon 2EI. For second part, you will be considering second part. So here if you will take section RA into X, here if you will take section RB into X, or RA into X plus M. So in that way you can do very easily. Is it clear? I feel you got it, Ajay. Fine. So guys, just like the session before you leave it. Tomorrow at 10 AM we are meeting for the mock test. Okay, be ready for that also. Okay. So for mechanical, civil, both the branches, we are coming with the mock test. So goodbye guys for this session. We will be sharing this PDF after the session within 10-15 minutes. You will get it on our Telegram channel, Mechanical by Dheeraj Sardana and Civil by Abhinav sir. So you can join both the Telegram channel to get the updates, to get the notes, to get all the PDFs. Ajay, you share with me the case. We can have a call on that and I will clarify you. Goodbye, guys. Thanks. Good night.